and quantitate the in the 3D in the micro 3D scale is difficult for the multi-phase flow because the 3D geometry is very complicated. So here we introduce a new approach of 2.5D. So is 2.5D means the variable micro model. So it's easy to visualize and quantitate. So for the fabrication of microfluidic chips and micro model with 3D feature, they usually use the old method as 3D printed. However, the 3D printed has a low resolution and the printing resolution and the material is limited. So it's impossible to build a 3D micro model as a is simplified. So the new method is fabrication the 2.5D micro model, and the advantage is the depth of the ratio of the flow to the flow body is easier to control. So we use the glass as material because it's transparent and high hardness and easy to modify. So the design, we will use the AutoCAD to design the 2D blueprint and then project to the glass chip. So the fabrication, we will fabricate the glass microfluidic chip following the standard hydrographic process and hydrofluoric acid etching. The etched glass plate was bond to a cover glass mostly by heating at 500 to 700 degrees Celsius for hours. So here is the process for the 2D micro fabrication. So they put mask on, they put several layers on the glasses. One is the mask, second is the photo resistance, and third is copper. So after several process, so we have the final product. So the limitation of the etching process is because the etching process is toward different directions. So if you use the etching for the 3D product, so it will be the shape is not ideal. However, we use for the 2.5D, so the channel and the pore grade, and it can be controlled very easy. So here is the fabrication of 2.5D models. There's obtain a shower flow by making use of isotropic etching of HF by controlling the distance between the pore and the etching depth. So it can control this etching depth to control the pore depth and the flow depth here. So as shown in the figure, so the to control the depth and the flow and the depth on the flow, so they can control the so that they can control the etching for the pore distance. So the pore distance is different, the flow depth is different. So we can create nearby pore connect by a flow which is not horizontal, which is not only horizontal narrower than the pore body, but also vertically shallower than the pore body. So this is the product under the microscope. So this is the flow between two pole body. This is the gram lab by the cover, so it's not etching by the HF. And yes, and next. So this is the formula of the height of the depth of the flow and the depth of the hole and then the pole. So for this formula, when we plug this formula, and this is the actually the blue triangle is actually data, and the dashed line is the formula. So it's a very small, very small mistake. So there were a couple experiments done on the 2.5D glass micromodel. One is the wetting phase impedition, and the second one is the emulsion folding. This last one is the ultra low IFT surface folding. For the wetting phase impedition in the water wet hydrogen receiver, such as sandstone receiver, after oil phase is displaced by water. Uncovered oil is often classified by two types. One is the residual oil, which is isolated oil drops trapped by the capillary force in the whole body. Another one is unswept oil, which is the oil occupies continual region unused by the water phase. So this is the geometry parameter of the 2.5D glass micromodel applied to these experiments. So we can see the parameter here of the flow, all the flow, and the depth of the flow. So this is also the 2D and 2.5D model experiments with oil viscosity less than water. Both experiments, the N-octans was used as the oil phase and the percentage into the micromodel before the water flow dye water was used to aqueous phase. So the picture B and picture C is the 2D and 2.5D 2.5D water flow respectively. So it's clear that showed in the 2D micromodel a pole body is either occupied completely by water or by continual oil phase. No isolated oil droplets trapped in the whole body was direct in the reality. Porous media was obsolete. So in the C for the picture C for the 2.5D model, almost every pole body trap isolate water droplets with water phase occupying the flow and the pole edge. It is easy. It's exactly that the theory described as in the 2A. So for the D and G is the water imbibition into oil statues. 2.5D micromodel at the different time. It can be observed that the water only flow along the flow and the edge of the channel without displacing the oil and in the point body, and isolated oil droplets are flow trapped in the point body. The flow direction is from the left to the right. So the second experiment is the emulsion flooding. The emulsion flow fluid is in the porous media was growing research area in the enhanced oil coverage and in the chemical food industry. A long-standing question is how the size of the non-wetting phase droplets varies spectrally in the pore media. Often was used as the oil phase in this experiment, and 1,000 ppm silica nano particle and 500 ppm 318 was added in the dye water as emulsion stabilizer. Oil and quantitous phase are co-injected at both and 7 ml per hour. So here we can see that the oil and the water was incoming into the 2.5D model from the left to the right. So you can see in the right side, the oil droplet is broke into a small droplet in the pore section. This is the under the microscope image of emulsion flow in the inlet, and 2 cm downstream in the figure 3, 3A and 3B. So we can see the image phase is very short distance close to the inlet, and the oil droplets will broken into a small droplets, but after 1 millimeter from the inlet, the droplet of the oil will remain almost the same. It won't change after the 1 millimeter distance. So this is how the size of the oil droplets change. So from in the beginning it's very big, and after getting into the 2.5D 2.5D micro model, it becomes small. And the last one is the ultra low IFT surface flow. So the enhance the oil recovery by injecting ultra low IFT surfactants is reported to cover more than 90% oil of a light oil receiver. So this is the surface flowing process in 2.5D models. A to C is the microscope image of the floating micro model from the upstream to the downstream, where we can visualize the distance water oil two phases from the oil water constant line in the C, picture C. Residual oil flowing to the front in the B, and and the microemulsion phase is in the far upstream. So the picture D to the picture G is the zoom image of a fixed region of surface done floating in 4-minute time interval to the to capture. So microemulsion can be observed generate from the residual oil in D and E, and then the co-floating with water phase like a belt in F, and the whole region was finally with neither the residual oil or the microemulsion was shown in the number G. So for the summary, the 2.5D is 2.5D micromodel is very easier to manufacture and control, and then the 3D models. And the 3D model is difficult to observe, and the flow in it, because it's the 3D model is very difficult. It's very complicated. So the 2.5D is such a simplified version of the 3D models, and so we can successfully finish the 3 experience with the 2.5D micro model. That's it. Thank you.